Hi students, welcome to another lecture video. This video will be on calculating enthalpy change in a chemical reaction and using bond enthalpy to do that. So a quick reminder on really what we're talking about when we mention the word enthalpy. Remember, enthalpy is the amount of energy stored in a chemical system. So if the enthalpy is high, then those chemicals have a high ability to release that energy as heat. If the enthalpy is low, they have a low ability to release that energy as heat. And then we can see from the way that a system here of reactants versus the system of the products, comparing those two groups of chemicals and the before and the after, we can see whether a reaction is really overall releasing heat or gaining heat or gaining energy, like if it's being stored or being released in this reaction. So it's the comparison between those reactants and products. Okay, so that's what we're trying to imagine with delta H, is to envision the change in enthalpy, which is this guy right up here. And the overall calculation is basically we need to figure out how much enthalpy was absorbed in the reaction and subtract any of the released enthalpy that gets released as a process in the reaction. And when we do that, we're able to calculate the change in enthalpy and determine whether this reaction was exothermic or endothermic overall. One of the things to remember is that when you go through the reactants, which are represented down here, and turn them into products, you must first break those chemical bonds. Every time you do a chemical reaction, you have to break a bond in order to form the new ones. And breaking bonds is an endothermic process by definition, because by breaking a bond, you're actually putting energy into that chemical to pull those bonds apart. So that energy then kind of gets stored in the separated atoms or parts of the molecule, and then once they get put back together and formed, you actually start to release that energy, and that's exothermic by definition. So this one will always be endothermic, that's always going to be exothermic. Once we calculate the overall process, and we do basically the breaking, the amount of energy put into the breaking process, the absorbing process, and we subtract the amount that's released when they're formed, then we'll be able to calculate, well, was this overall reaction exothermic or was it endothermic? And that's why that calculation up here exists. So let's go ahead and use some bond enthalpy values that we get out of this table here and use that to calculate the overall change in enthalpy from reactants to product. Remember, we're taking the reactants here and we're turning them into products over here. So the first thing to do is to investigate our different chemicals, the CH4, and see what type of bonds those are, and then the O2 and see what the types of bonds those are, and start to do a little bit of summing up in some pretty easy arithmetic. So the first task is to, as you see in this table here, identify the bond type. So the bond type, what's the bond type in this carbon-hydrogen molecule called methane, CH4? Well, it's really just a C to H bond and another C to H bond, and they're all the same type of bond. So one of the bonds that are breaking is C to H, and because that's all there is in that molecule, that's all we need to really write down for CH4. Over here we have the O2, and there's two of them, 2O2. It's important that the balanced reaction is represented up here. You'll see why in a minute. But the only bonds that are in the 2O2 chemical here, the oxygen chemical, is this double bonded oxygen. Now our next step is to calculate the amount of bond enthalpy within those bonds. So we're going to go ahead and actually, it's not really within those bonds. So our next step is to calculate the bond enthalpy, or at least the energy required to break the bond of a double bonded oxygen and a C to H bond. So the first one is 413. We get that from the table right up here. The next one is the oxygen bond right up here, which is 495. So now that we've calculated or just looked up in the table how big that value is, how many bonds are broken? Well, in CH4, there's 1, 2, 3, and 4. So there's 4 bonds broken. for this chemical reaction. Over here, we have one bond broken over here, but because there's two of these, then there's another one in the second molecule. And this is the number of bonds broken here. Now, it is important to remember the units just briefly. It's kind of more in passing to note this. The kilojoules per mole unit for enthalpy means that this is how many kilojoules, or in the terms of what a joule is, it's an amount of energy, but this is the amount of energy required to break 1 mole of the C to H bond or any other bonds that are in here. And remember, 1 mole is 6.02 times 10 to the 23rd things. And so if we have 1 mole of C to H bonds, then we had 6.02 times 10 to the 23rd C to H bonds broken or formed. So in this case, they're broken, but it actually doesn't matter which way they go. It'll be the same value, broken or formed. So that's just something to note, that it is actually representing a mole for that actual value. This is a real value of how much energy it takes to break 1 mole of those bonds, not just one. So now the final step is to do a little bit of simple mathematics, the total enthalpy from each bond type. So I'm going to basically say how much bond energy, or enthalpy really, is required to break a mole of those things. And how many bonds did I break? And then just multiply those two things together. So it's going to be 413 times 4. And then over here, 495 times 2. So for my values, I get 1652 and I get 990 on the oxygen bond. And then the final part is, this is a typo here, the total enthalpy from the bonds broken or formed, which is really just adding these two things together, and I'll get the total broken amount over here. And that value is 2642, just adding those together. Okay, so now I know how much energy was required to break the reactants apart into their component atoms, and then to rearrange them and put them together as products. Now I can do the bond enthalpies for those formed bonds. So what I'm going to do here is the exact same steps. I'll kind of go a little faster. The first step is I'm going to go oxygen to hydrogen bond and look up how much I get. There it is in the table. Carbon to oxygen double bond. There it is in the table, 799. Now I'm going to count how many bonds are broken. So there's 2 oxygen hydrogen bonds per water molecule. There's 2 in there, there's 2 in there, and there's a total of 2 molecules. So there's 4 total bonds that are broken, or sorry, formed. Now, how many of these CO bonds are generated? Well, there's only 1 molecule, but there are 2 bonds per molecule. So 2. Now I'm going to go ahead and do the math. Okay, now I have my math calculated here for the bonds formed and the bonds broken. And I'm going to just add those two together to get my total enthalpy for the formation of these molecules. And that's going to be 3,450 kilojoules, right? So if I compare these two values, I can already see that forming produces a lot more energy, this is the released part, than the amount that was absorbed to break the bonds. So I can tell that I'm going to have more released than was absorbed. But I'm going to go ahead and do my math here so I get a good value. The delta H of the reaction is going to be the amount absorbed, 2642. It does matter the order that you put these in, so make sure you don't mix those up. 2642 and 3450. I'll go ahead and calculate that. And the answer is negative 798 kilojoules. Okay, so there is a release overall as one of these reactions goes. At least a mole of those reactions go. We'd sort of say, like, for every mole of methane that you add, then you get 798 kilojoules of energy out of that, because the delta H is negative 798 kilojoules. And the reason it's negative is because when I subtract by this equation the number absorbed by the number released, I get a negative value because the number released is larger than the number absorbed. Because of that way that we've written the equation, we know that any delta H that is negative is going to be exothermic, and any delta H that is a positive number is going to be endothermic. So we already can tell this is a negative value. So is this reaction endothermic or exothermic? It is exothermic because it is negative, but also because it clearly releases more energy than it absorbs. And this makes sense too, because this is the burning of a fuel. Methane is a fuel. It's like propane or gasoline or anything like that. When it reacts with oxygen, it explodes, it creates heat, and its products are carbon dioxide and water. And as a result, I actually release more energy than the energy I had to put in to break the bonds. So that's how to predict the total enthalpy change in a chemical reaction using these bond tables here, using the chemical bond enthalpy values for each bond. And I hope that was helpful.